we should be able to go ahead and get started. We're going to talk about just what is deep learning, why do we care about it? How is it compared to machine learning, things like that. And then afterward, we'll kind of dive into the artificial neuron and all that good stuff. Okay. So what is kind of the idea behind deep learning? Okay, so you think about deep learning, right? So deep learning now is used in a variety of different cases. Okay, and a bunch of different fields are starting to use it, right? And deep learning itself, the crux of what we're trying to do is we're trying to essentially make human level decisions, right? And pretty nuanced human level decisions. And because of that, we're going to try and automate human level decision making. Okay, that's really what deep learning is trying to do. Is we're trying to automate human level decision making. All right. And it's used in various industries already, right? So for example, we can kind of speak about one particular example being like the healthcare, right? Because I'm in healthcare, so it's easy to kind of talk about that. But for example, like in healthcare, right? Various insurance plans are starting to use these deep learning models to automate things. So for example, I can kind of speak about the prior authorization space. So if you think about a prior authorization, it has to be approved by the healthcare insurance. And usually the way insurance providers do this is they have medical professionals on staff, right? These medical professionals, as you can imagine, are not cheap, right? You need to have them on staff because what they're going to be doing is looking at your prior authorization for a medication. They're going to be comparing it against a known set of criteria, and they're going to make a decision on your prior authorization whether or not that medication is going to be approved by the plan. If it's approved, the insurance provider is going to pay for it, and then we as the patient get the medication. If it's denied, unfortunately, we do not get the medication, and a kind of alternative treatment needs to be done, right? Well, these insurance plans are realizing this is really expensive to have these many, healthcare professionals on staff that long, right? Because, again, it's expensive. So what they're going to try and do, and what they've done already, and some plans have done this with some success, right, is pretty much make a type of essentially almost like an LLM, right, to look at the healthcare questions that are on your PA, compare that against the known criteria, and then that model can pretty much make a decision on whether it meets the criteria or not. And then all the healthcare professional has to do is just sign off on the final decision, right? So there is some human level interaction, but it's going to be at the very tail end, way downstream. And because of that, as you can imagine, the healthcare provider does not need to look at every question, look at the answers, look at the attachments, look at all that good stuff. It just makes that final sign off on it. And this has been chosen. It's been working fairly well for some plans. Some plans have been getting into hot water for it, but these LLMs can be able to automate that decision making that normally healthcare providers can normally do, right? So that's one example. There's other examples too. So for example, we're in the finance space, right? In the finance space, one example that I really enjoy is something like Bloomberg, right? Bloomberg, if you don't know, is kind of like an online kind of website. They have an app. And in that app, if you day trade, for example, you can go into the app and you can type in relevant information. So you can look at, okay, who is the CEO of this company at this point in time, right? The app will be able to return all the information for you. Or if you want to know certain stock prices at a certain point in time, or what other kind of financial terminology you're looking for, they have it, right? The issue is, and what Bloomberg realized, right, is that Bloomberg realized that no off-the-shelf model, so not like GPT 3.5, 4, whatever it might be, nothing from OpenAI, nothing from Meta, Google, they weren't really necessarily trained on financial data, right? So because of that, what does that mean? That means that these models don't really understand the nuances of that financial lingo, right? Similar to healthcare, right? Healthcare and finance, any different kind of company has their own kind of like talking, right? So when you think about finance, for example, right? So finance, what Bloomberg did is they pretty much kind of made their own GPT model. It's called Bloomberg GPT. Funny enough. And what they did is that model is actually fed into their application. So whenever a user kind of hits that app, right? What they're doing is they're looking at hitting the application, and the GPT model is going to return an answer. But that GPT model has been trained on all of Bloomberg's financial data. I mean, they're sitting on a wealth of financial data, so they figured they'd use it, right? So that's like another example, right? But other examples too. For example, like self-driving cars. This is something that Tesla does a lot of. So those of y'all who really love computer vision, right, or CV, that's going to be your MO, right? Self-driving cars, computer vision. I'm here in San Antonio. Whenever I'm driving on the highway, you got to watch out for other cars. You got to watch out for traffic signs. You got to watch out for lights. You got to watch out for potentially people. I mean, tons of things you have to watch out for. And these self-driving cars are trying to automate that, right? But regardless of what we're doing here, so I'll give you a few different examples, right? But the big thing is, right, that these models can really do, or these deep learning models, they really do support and do very well, is going to be multimodal data. So what do we mean by multimodal data? It can understand text data, vision data, audio data, right? As well as traditional tabular data, right? And it can do this very, 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 very well. Okay. So for example, you have the GPT models, which do like text to text. But you have other models, for example, like Stable Diffusion, which go like text to image, right? Or you have speech to text models. So for example, something like Siri, right? When you talk to Siri on your phone, if you're an Apple user, you say, Siri will do this, and Siri will actually write out what you're saying, right? So speech to text, right? Again, all of these are different types of applications, right? So you have things like Siri, you have things like ChatGPT, Dolly, Stable Diffusion, Midjourney, right? All these different examples that come up that hopefully maybe we kind of heard of and are familiar with. And a lot of what we're going to be doing today is going to be kind of the starting point for that. Okay, so something to keep in mind there. Oh, I have a question, Santosh. So I believe we use decision trees as well to tackle such cases, taking decisions. How is it different from that? Is the type of data we deal with? Yeah, very good, Santosh. That's a great question, right? That's a very good question. So you think about so the thing with these kinds of decision tree models, right, is the decision tree models will first off are really only going to work on tabular data, right? So it's got to be some type of array-like structure, right? So it's got to have features, it's got to have rows, right? Kind of data that we've already seen before. Now you can do that if you can make tabular data from text data, from video data, potentially from audio data, depending on how you set it up, right? But the thing with these decision trees and what they really struggle with is trying to understand a quote unquote nuance in the data, right? So for example, if you're trying to predict the next word, right, in a sentence, right? To understand what the next word should be in a sentence, you need to understand some previous context that happened before that word. So for example, if I gave you an example that said, the dog went to the park and blank, right? What should that blank be? Right, that blank should really be dependent on things like dog and park and right? The previous words that happened in the sentence, right? So that next word prediction, right? The decision trees, we can probably make something kind of work there as far as like what that next word should be, but it really is context dependent, right? Those decision trees don't really understand the nuance and how those words will relate to each other. I mean, it can kind of get some idea. Maybe like if dog appears next to bark a lot or cat appears next to meow, things like that, right? But understanding things in terms of like a long dependency, right, will be really, really, really tricky for decision trees to do. So decision trees are really going to kind of struggle with like traditional like text data, for example, right? Potentially even like video data, right? That can also be something where it's going to struggle, right? Our image data, I should say. Okay, so it really is it's really data dependent, but as well as I would honestly say, what kind of decision are we trying to do? It's kind of the big thing. So traditionally, when you're working with like text data, video data, audio data, the traditional machine learning models, they can do similar things, right? But they won't be able to do it as well as say a convolutional neural net for like images, right? Or even as good as a feed-forward neural network. Okay. And that's a conversation we're going to have at the very end of class is what happens on tabular data, for example, right? Because what you're suggesting is decision trees work really well, right? But for example, like on tabular data, right? It's been shown. So when I say tabular data, I'm saying, for example, like imagine you're trying to predict a credit card default, right? You might have a feature that has, I don't know, gender, another feature for income, another feature for zip code where they live, another feature for credit card score, whatever it might be. We can take all those features and we can predict on whether a certain individual is going to default, right? And that's what's called traditional tabular data, right? We have features, records, and we have a target, right? There's been a lot of research that's shown that on that kind of data, decision trees, like what you're suggesting, actually do extremely well. And honestly, they do better than neural networks. Usually the lift that you're getting from a neural network is little to none on that kind of tabular data. And the reason for that, right, is because these decision trees can understand those interactions fairly well, right? There's not really too much that needs to be done there that a decision tree cannot handle, right? So on tabular data, these decision trees are going to do extremely well. So again, predicting credit card default, predicting, I don't know, sales for a particular item, maybe forecasting, some things like that, they'll do great. But it's when you start having these multimodal kind of data that are not necessarily tabular a priori, things like text, text, audio, visual, that's really where these traditional machine learning models are going to start struggling. And the tasks that we can do with them is really where it's going to start struggling. And again, it's we're trying to understand context in the text, understand context in the images or the sound or the video. That's really where those decision tree models are going to struggle. So does that make sense on what we're saying there? It's a little bit of kind of a long-winded, but I want to make sure. It's a very good question. We're going to talk about it more towards the end, but is that okay? Cool. Sounds good. Sounds good. Yep, for sure. Definitely. Awesome job, y'all. Very good, very good. So again, what is deep learning here too? Yeah, so deep learning, right, is a subset of machine learning, right? And the idea with deep learning, right, is that it's going to use primarily the what's known, right, as what's called an artificial neural network, right? We're going to use neural network architectures to do those decisions. And these neural network architectures can really understand complex relations between the input and the output, okay? Wherever the input and output is. All right. Now, deep learning with these artificial neural networks is kind of motivated by these biological neurons, right? The biological formation of our brain. Now, again, I have biology friends, people who work in computational biology, who say that this is not necessarily fully right. But again, it's kind of a loose interpretation. Okay, back in the 80s when these things are being built, that's really kind of what the motivating factor, I would say. All right. So again, it's a loose interpretation of it, but we're trying to mimic our human brain structure whenever I'm speaking to you, for example. I know the next word. Whenever you show me an image and you ask me to classify that image, we know we can do that with what we kind of know in our brain, with what a 4 looks like or what a cat looks like, things like that, right? We want to try and make these deep learning models do that same kind of decision making, okay? And we want to kind of set them up to do that, all right? And again, deep learning can do this for not just traditional tabular data, but also other kinds of data as well, all right? Which again makes them very powerful. So just something to keep in mind there, okay, y'all? These deep learning models, or deep learning in general, is going to be a subset of machine learning, but we're also going to be using artificial neural networks to mimic the human brain to make those decisions, okay? So that's kind of the idea there, all right? And then deep learning also can support like automated feature engineering depending on how you actually hook it up, which is also pretty cool. Whereas in traditional machine learning, you almost have to do that feature engineering yourself, right? Which is kind of time consuming, and deep learning can kind of almost understand those relations almost implicitly, which is pretty great. Okay. So again, kind of a question to ask ourselves, right, is how to identify a deep learning problem, right? When should we use deep learning? When should we not, right? This is a great question that we need to ask, and it's kind of what Zen is getting at, right? Like, when should we actually understand, when to use these kinds of models, right? So what I always recommend is it really depends on the problem, but you really want to try and look at complex patterns, right? Yep. So when I say multimodality just means multi modes of data, right? So not just tabular, but video data, audio data, text data, sound data, things like that. Things that are not necessarily inherently tabular to begin with. Yeah. So like unstructured data that maybe we have not seen up until this point. Awesome. All right. So complex patterns, that's pretty much what we're trying to do, right? So for example, you think about the convolutional neural net, which you're going to see in detail in I would say about 2 weeks, right? But what these neural networks are trying to do is understand, okay, if I look at an image, what does a nose look like? That's kind of the first layer. The second layer is going to be like, okay, what does an eye look like? The third layer is going to be like, what does an ear look like, right? And eventually it's going to realize, oh, I am looking at a face, right? And then with that face, it's going to try and maybe classify certain images into humans or not, classify certain images into dogs or not, yards or not, whatever it might be, right? We're trying to understand spatial relations, right, in these images. So for example, that's kind of what these complex patterns, right, that we can kind of do as humans fairly well. We want to try and teach these architectures to do the exact same thing, okay? Again, this is kind of one particular problem. So for example, like in images, okay? But I gave you another example with like text data when you're trying to predict the next word in a sentence. That's also going to be like a next word prediction problem that LLMs can handle fairly well, okay? So something to keep in mind there, okay? We're trying to understand these complex patterns, complex representations. They are not necessarily inherently tabular to begin with a priori. Once you have those two kinds of things put together, you're probably looking at a deep learning problem, depending on the task at hand, okay? And with that said, right, like I said, right, these artificial neural networks are trying to mimic this human brain behavior, right? So in our human brain, we have what's called a biological neuron, right? And again, our brain has a large network of them, right? They're kind of all interlinked. They're all kind of storing information and they're talking to each other, right? They're sending information to each other back and forth. And what they're trying to do is they're trying to learn. We're trying to go from one point A to point B, and we're going to try and transmit information as quickly, as swiftly as possible, but also as efficiently as possible so that we can do whatever it is that we're trying to do. Whatever task that we're trying to do, we're going to try and accomplish it and we're going to learn, right? We want to send information and we want to send the best possible kinds of information, right? Oh, that's a great question, but yeah, that's a great question. So what we're asking here is, it doesn't mean deep learning problems require a really large amount of data relative to traditional ML. That's exactly right, man. That's exactly right. And we're going to talk about that here in the next couple of slides, but just as a preview, right? So deep learning problems can really can overfit fairly quickly, right? So these neural network models, because they're so big and powerful, if you feed a small data set, if you make it too deep or too big or too powerful, it can really start to overfit really quickly. So traditionally with these deep learning models, you want to try and feed in as much data as you possibly can to prevent the overfitting from happening, but also to allow as much nuance in the data to be captured as possible, right? So to understand as much context in the images that are there, understand as much context in the text data that's there, understand as much context in the sound data that's there. That's going to be what you definitely want to do there for sure. So it's going to require tons of data, a lot of data in order to train them compared to traditional machine learning. And we'll talk about that more here in a second, but that's 100% right. That's a great question. Okay. I think that TA's answering the next question here, so I'll let him do that. But does that make sense? But that's a really great point. So I want to make sure we're on the same page there. Awesome. Very good. Very good. Okay. Okay. So again, no. So the biological neuron, right? It is we have our brain's made up of a bunch of them, and it's sending information to and from each other, right? And we're trying to pretty much just gather the best information possible to do downstream tasks. Okay. That's what our brain does, right? And our brains will transmit information from one point over here to another point over here, right? We want to try and make a neural network structure to do exactly that. And we're going to do that by means of what's called an artificial neuron. Okay. An artificial neuron, right, is essentially going to be a mathematical function or a mathematical equivalent of a biological neuron. Okay. It's going to be the mathematical equivalent of a biological neuron. And essentially what we're trying to do here is these artificial neurons are going to receive information the kind of a similar way that the biological neurons do. They are going to kind of update that information on these highways, which we call weights, right? Or parameters, right? These weights or highways of parameters, right? They're pretty much taking information and they're sending it to and from other neurons, right? These W1s are what are called weights. And once we kind of take that information and we send it, we're going to make a final decision in our output, okay? And what's going to happen is this artificial neural network, which we're going to talk about here in a second, right, is going to be made up of a bunch of these neurons where we're going to receive information. We are going to try and understand that information on these kind of highways, these information highways. And then we're going to do some processing and then make a final decision on the output. Okay. Again, very similar to what biological neurons are doing. We're sending information from point A to point B. Okay. And then we're saying, how are the weights decided? Are the weights decided automatically? Great question, bud. Great question. So the weights themselves are going to be dependent on the number of neurons that you have, as well as the number of hidden layers that you have, which we'll talk about here in a second, what those are. Everything we're going to be talking about today is going to be through what's called a feed-forward architecture. Okay. So what does that mean? That means that every neuron in one layer is going to be connected to every neuron in the next layer. So for every neuron that you have in one layer and the next layer, they're all going to be connected by weights or highways of information. So it's going to be dependent on, to answer your question, how many neurons you have in your architecture, as well as how many number of hidden layers you have in your architecture. And the weights themselves, right, are kind of initialized randomly according to the normal distribution, but those weights are going to be learned throughout the training of the neural network. Okay. And we'll kind of expound on what that means there. Those weights are going to get updated by means of what's called backwards propagation. And we're going to learn them so that our model can make the best possible decision. Yep. Awesome. Okay, that's a great question. Okay, so now again, the artificial neurons send information from point A to point B. We got an input at A, we got an output at B, and we have information, number crunching, then do the output. Okay. And what's going to happen is that our artificial neural network, right, is going to be made up of a bunch of these neurons. Okay, which gets us to the next slide. If I can click the next button, there you go, which is going to be artificial neural networks. Okay. So what you can see here is have each one of these guys is going to be a neuron. Okay. We're going to have a neuron. So the squares and circles are all going to be neurons. Okay. And our artificial neural network is going to be made up of all of these different neurons with all of these different highways connecting them to each other. These highways are going to be what are called the weights, these WIJs. Okay. The parameters of your neural network. Okay. So weights and parameters kind of mean the same thing. Okay. They're the highways of information. And our artificial neural networks, right, are going to be built up of what's called an input layer. We're going to have one or more hidden layers, and then we're going to have an output layer. Okay. The hidden layers themselves, can vary depending on the architecture. So imagine that the number of hidden layers that you have, the number of neurons that you have, are a hyperparameter for your neural network, right? It is a kind of decision that you need to make before training. And you want to choose the number of hidden layers and the number of neurons to prevent overfitting from happening on your data, but also getting you the best possible result that you want, right? So you want to minimize loss without overtraining on your data, pretty much with the hidden layers and the neurons. Okay, so you want to choose the ideal number of hidden layers, the ideal number of neurons to enable you to do so. Okay, this is very similar to how you would maybe train an XGBoost model, right, or cat boost, these boosted trees, right? You want to choose the number of trees that you build out in your model and how deep each of those trees are to get you the best possible metric that you care about, but also without overfitting, right? So it's a very similar idea here. In the same way you kind of choose the number of trees, you choose the number of layers, how deep those trees are, or how many neurons you have in those layers. Okay. Guru says, is my understanding correct? So each neuron is a function, could be linear, nonlinear, or decision tree. Oh, very good question, but so it's not a decision tree. Yeah, that's a great point. So it's not necessarily a decision tree. Yeah, so a neuron is essentially going to kind of contain information, and we're going to send that information to another neuron, and in a nonlinear way, which we're going to talk about what that means here in a second, via what's called an activation function. Yeah, so not a decision tree. It's going to kind of store information, and it's going to send information to another neuron, right? Via a nonlinear function. And I'm going to show you what that looks like here in a second, but it's not going to be a decision tree. Yeah, that's a really good point. So this for now it's a mathematical abstraction. It's a mathematical function that's going to kind of hold information and send information. That's what we can think about it for now. Okay. But that kind of gets me to my next point too here, y'all. Okay, so artificial neural networks, they're made up of input layers, hidden layers, output layers. Each one of those layers is going to have neurons. They're going to have a bunch of weights connecting each layer to each other, all the neurons to each other. Okay, and because of that, all of that kind of system or architecture that's put together here. Okay, it's meant to mimic the human brain. Okay, so whenever somebody asks you what is an artificial neural network, okay. Whenever somebody asks you that, the quick elevator pitch, okay, is that ANNs, or artificial neural networks, are mathematical abstractions of the brain. Okay, they're mathematical abstractions of the brain. We have all these neurons. We have all these information highways connecting the neurons to each other, and we're going to try and understand whatever task we're trying to understand to do the output. Okay, so maybe we want to understand what the next word in a sentence should be, what this image should be classified as, what this sentence should be classified as, what this sound wave should be classified as, things like that. Okay, and we're going to use these weights to pretty much try and understand the best possible information that can be understood to do whatever downstream task that we want to do. Okay. And like I said to y'all, these artificial neural networks, okay, are going to be all feed forward. Okay. They are all going to be feed forward in this class. Okay. So everything we're doing in this point is going to be what are called feed forward neural networks. Okay. So in this class, okay, what does that mean? That means that every neuron in one layer is going to be connected. It's going to be connected to another neuron in the next layer. Okay. So they're all going to be connected to each other. Okay. Via weights. Okay. And these weights are going to be updated throughout training. All right. So feed forward just means that everything is dense. Okay. So every neuron is connected to another neuron. All right. This is what we're going to be focusing on in today's class. And I'm going to show you the ideas of what forward propagation is, backward propagation, gradient descent, loss functions, all these optimizers. I'm going to show you what those mean via the viewpoint of a feed forward neural network. That way, when I would say in about 2 weeks, when you start talking about convolutions and you start talking about recurrent neural nets, and eventually when you start talking about the transformer, right, you're going to understand what all of those concepts mean via kind of what you learned here. Okay, so what we're doing today is going to set the foundation. Okay, so you want to make sure that we understand all the different concepts from this viewpoint. And then once you understand this viewpoint, you can kind of get to the next one. Okay, you kind of have to learn how to walk before you can run. Okay, so something to keep in mind there. Okay. So do we choose this function or is it derived during the learning process? So I'm assuming you mean kind of like how we send information, like the neurons. So the neurons are just going to store information, and they're going to send it. They're going to send information, and they're going to send it through means of what's called an activation function. And that activation function is one that you can choose before training. So that would also be like a hyperparameter. I want to talk about that, what that means in a second. Yeah. So there's nonlinear activation function. You can definitely take it, and we can choose that beforehand, for sure. They're about saying, can neurons be connected to others in its own layer too? Ooh, that's a great question. But so usually in traditional feed-forward neural networks, we don't have any loops, right? So if they're all going to be connected, so if they're one neuron in one layer is connected to another layer, is connected to another neuron in the next layer. So not necessarily to any neurons in itself. So all the weights we're not going to see any of like this, for example, right? None of that. We're not going to do that in this class. Everything in one layer is going to be connected to another neuron in the next layer. Yeah, so no self-connections, I would say. That's a really great question, at least in this class. So we want to motivate it just simply through the feed-forward architecture. And then once we kind of get this down, then we'll kind of start seeing some more fancy stuff in later modules. So things like recurrent neural nets, convolutions, transformers, graph neural nets, all those things are coming up for sure. So that's a great question. Which kind of brings me to my next point, right? This idea of what are the kinds of neural networks that are out there, okay? So, so just so we kind of have an idea where we're going to, okay, y'all? So the first thing we want to try and understand is that today, we're going to be talking about the artificial neural network, or what's called a feed-forward neural network architecture, okay? Why do we need more layers? Is it trying to get closer to the target in each layer? Oh, great question, bud. So ideally with the neural networks with more layers, right, is that we're trying to essentially minimize the error that our neural network is doing, right? So the idea behind neural networks is we have some error between our target and our prediction, right? And in theory, if you add more layers, you allow for more weights, you allow for more parameters in your neural network. So if that's the case, your neural network can, in fact, learn more information, potentially. And if you can learn more information, you can make better predictions. If you make better predictions, you can minimize the error, right? So to your point, you can add more layers to enable your model, to enable your model's predictions or your network's predictions to get closer to the target. So that's one reason why you can add more layers for sure. But there are trade-offs to that, which we'll talk about more later on in class. Because if you allow for more layers to happen, you allow for more calculations to happen. And what happens with those calculations can lead to unfortunate or bad training practices. So, and I'll show you what that means here in a second. All right, but kind of going back here. So the types of neural networks, right? So we have the artificial neural network, which is going to be the feed-forward architecture, which we just talked about. So again, everything's connected, right? And it's all flowing forward. All right. We have also what are called sequence-based models. Okay, so sequence-based models are going to be things like recurrent neural nets, for example, along short-term memory models, as well as GRUs, gated recurrent units. These models are what you're going to learn about in, I think, 2 weeks. Again, we have to understand what's going on here before we can do that. Because what's going to happen here is that these models are going to start these are really going to start being really great when you have to understand things like text data, for example, or sequence-based data, things like time series, right? Things like that are really going to be what you want to look at with these kinds of things. But then you're also going to have things like convolutional neural networks, right? So this is going to be things for like image data, right? So image data are going to be really powerful when you want to try and do like image classification, right? So convolutions are really where that's going to shine. But then we also have what are called the transformer. Okay, this guy right here, y'all, I want you to maybe star it. It is a super, 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 super important architecture. It is the architecture, honestly, that is the gold standard in a lot of research that we're doing today. The transformer really is what kind of the backbone behind like an LLM, for example, right? And a lot of what we're doing there is kind of the crux of a lot of different research methods kind of put together, right? So, for example, with the transformer, people like in NLP use it, but people also in like CV use it, right? So the transformer is almost kind of like a convergence point for a bunch of these different fields of machine learning. And honestly, it hasn't really changed too much, right? It's been pretty powerful. It's kind of stood the test of time since at this point, 2017, right? And it's a very powerful architecture, and it's one that we're actually going to dive into in your NLP modules. And so in your NLP modules, we're going to dive into this in full detail to make sure you understand it. It's a very, very powerful thing. It's pretty much like almost like 2 hours of content just because it is so important. Okay. But that's coming up down the pipeline as well. But we also have things like graph neural nets. This is actually another thing. So those of you who are maybe going to be taking modern ML architectures is where you're going to start seeing graph neural nets. Graph neural nets are really powerful because you start using them, for example, like in recommendation algorithms, right? If I'm connected to somebody else and that person is connected to a friend, if we're friends, should I also be friends with this person that my friend is connected to, right? So you can do that via nodes and graphs, right? So that's going to be a kind of another architecture that you're going to be seeing in the next few weeks. All right. So all of this, I just want to paint the picture for you that, this is kind of where you're going. Okay. But we know before we can get there, we need to make sure we understand fundamentally, what we're doing in the simplest setting, which is a feed forward network. Okay. If we understand what backpropagation is doing here, what gradient descent is doing here, what loss function is doing here, everything else after this will be fairly, will kind of follow with some minor tweaks. Okay. So again, something to keep in mind there. All right. But again, this is where we're going. It's very, very powerful stuff. All right. So just a quick little summary here to y'all. Okay. So remember the neural networks, right? They're trying to mimic human brain behavior. Okay. We are going to try and essentially make human level decisions. Okay. So a lot of what these neural networks are, these deep learning models are going to be inspired by the human brain. Okay. They're inspired by the human brain. All these neural networks are connected, right? Via a bunch of neurons have all these weights that are connected with each other. And we're going to try and make those weights as strong, as powerful as we possibly can to learn as much information as possible in order to do any downstream tasks that we care about. Okay. So again, just something to keep in mind there, okay? These neural networks are almost they're a deep learning model. They're very similar to these machine learning models, but they can handle other kinds of data very, very well that maybe these machine learning models cannot, okay? So some of the questions that were asked are very, very good questions. So something to keep in mind there. And then also, and just like we just talked about, right, is that these neural networks cannot learn these rules if your data set is small, okay? I think somebody would just ask that. It's a really, really good point. So we have to make sure we understand that you need a lot of data for these models. Okay. So can we think of hidden layers of neurons as a chain of traditional ML models where each of the input features are output from the others? I mean, definitely, I like your latter way of thinking about that, bud. So like, you go from the input to the output. Traditional machine learning model, it depends what you mean by that. There is some calculations being done on those hidden layers, right? but it may not necessarily be the exact same calculations that are being done, like in a decision tree, for example, or logistic regression, right? But there are some mathematical calculations happening in those hidden layers, right? That's kind of why they're called hidden, um, that are then going to allow us to make a prediction on a downstream objective, right? But how those calculations are being done might be a little bit different from how a traditional machine learning model is doing it. So I like it's a very close, but it's some minor nuanced differences that we have to keep in mind there with your analogy. It's a chain of mathematical calculations that are being done that are similar to ML models, but it's not like traditional machine learning models are taking place inside of those neural networks, inside of the hidden layers of the neural network. So like there's no boosted trees going on, there's just regression, things like that. That's a great question. Alrighty, yeah. So, like I said, again, really good point that was asked earlier about data sets being small. You definitely want larger data to train your neural networks. Okay. Usually, it really is kind of data dependent as well. But you want on the order of millions at the very least. You can do toy examples on smaller data sets. It's perfectly fine. But in practice, you definitely want larger data to allow your networks to understand all the complex relations that it possibly can. Okay. So that's the first thing. You want larger data. Um, the second thing that you need to keep in mind with these neural networks, right? And this is something I always like to tell people in this class because it's a really, really good point to kind of think about. But you think about neural networks, right? And again, we've kind of been talking about this a little bit in the Q&A already. But what I want you to think about, okay, is when you're in practice, when you're doing your problems, whenever you're doing homework assignments, whenever you're interviewing for jobs, okay, is if you use a neural network, or let me rephrase the question. If you get a problem, okay, you really want to ask yourself, what is the best possible solution that I can use, okay, to solve this problem, okay? If that neural network involves things, if the neural network, if the problem needs or necessitates the need for a neural network, fantastic. Definitely use it. I'm all for it, okay? But if the problem that you're looking at, for example, only involves like plain or simple tabular data set, like you need a neural network to do that, right? Or would a boosted tree do just as good? Okay. Or heck, what about group bys, right? Like would group bys work on this tabular data, right? Maybe some simple rule-based logic might work. Okay. What I'm trying to get at, y'all, is that these neural networks are not silver bullets. Okay. And as strong as they are and as powerful as they are, they do come with some cons. Okay. So you need to keep that in mind. Okay. Please, please, please keep that in mind. So whatever problem you're trying to solve or you're trying to figure out, okay, ask yourself, I know neural networks are there, but is it absolutely needed? If I'm trying to predict credit card default, I probably don't need to make a feed forward architecture, right? I can just use like a simple thing like a boosted tree or heck, even logistic regression, right? If I'm trying to do like a regression problem, try linear regression first, right? Like do not jump straight to neural networks. And another thing to understand too, when you're doing these neural network problems is if you do choose to use a neural network for a particular problem, you want to understand why, okay? Oftentimes, y'all, like whenever I'm interviewing people at my company, they say, "Oh, I use this BERT model to do text classification, and it got this result. Here are my metrics." I'm like, "Awesome, fantastic. Why did you use BERT? Why did you use these big language models to do that?" And responses that I gotten before in interviews is, "Oh, I just looked it up on Google, and that's how they said to be done." That's not an answer. Okay, in fact, that's a bad answer. Okay. The idea being, right, whenever you're trying to solve problems in real world, in industry, right, in just all real world data problems, right, you always got to have a baseline. So simple rule based logic, right? Have you tried that? Group bys. Have you tried something simpler, like maybe like a naive Bayes for a text classification? Have you tried maybe like logistic regression? Have you tried something smaller first to make sure that that works? And then after you realize that that cannot work and you tested that thoroughly, then can you move on to these neural network problems? You can move on to the LLMs, you can move on to the convolutions, the transformers, all that good stuff. Okay. The reason for that too, y'all, is that because remember, your job as a data scientist or as a machine learning engineer, your number one job is to provide value to the business. Okay. That's your number one job. I don't care. I'm pretty stout on that. The tools that you use to provide value is mute. Okay. Whether if I make a logistic regression that's easy to train, it gives me fantastic results. It's easy to productionize, and it's very efficient to do so. And I provide an increase of $1 million in revenue or something to another company, right? Do you think the company really cares if I do that versus the neural network? Probably not, right? Your number one job is to provide the best possible solution to solve that problem, okay? And oftentimes what I see happening is that people come on my team and they want to make a neural network. And I'm like, why? Do you need to? Okay. Will this simple solution work? And I kid you not, there's one problem that we had for a person who came on our team. He built out this fancy neural network to do some type of classification. I actually showed him, I paired coded with him how to do it with a group by. And the group by worked. And you can do the group by in SQL, right? And again, the company's not going to care how you provide that solution as long as you provide the best possible solution. And it works and it provides value. Okay. Another thing to keep in mind too, these neural networks, okay? And what I'm trying to get at with this previous statement is that neural networks are hard to productionize, okay? They're very big. They're very computationally expensive, right? Sometimes you need GPUs to actually build them, okay? For example, if you're trying to build out your own language model, that might not be practical, okay? And the reason I say that is because depending on the company that you're at, your company may not be able or may not be mature enough to actually productionize a neural network architecture. Okay. I know that because my company was actually in that state until a couple of years ago. Okay. Not every company is going to be mature enough to be able to handle that. Okay. If you're not cloud-based at your company, for example, good luck. It's going to be really hard to do that on a Jenkins worker, for example. Okay. You're going to run out of memory pretty fast. All right. Some companies may not have Kubernetes set up, unless you're going to do it yourself, it's going to be really, really hard, right? So trying to productionize these neural network models can be very tricky. Now, if you're a company like Google, Amazon, PayPal, all these big tech companies, 100%, you're going to be fine. Like you probably can do it, right? And I hope all of y'all get there, right? But if you don't, for example, you have to keep in mind that these neural networks are very powerful, but they come at a cost, okay? And we, as the data scientists and machine learning engineers, need to understand that cost and need to weigh that cost versus other solutions that are not as expensive and that provide just as much value as the neural networks.